Okay.
Hello, Hyungbo. Hello, Bayo. Hello, Claudia.
Hello, Christopher. Hi.
Hi. Nice to see you.
Yeah, thank you for coming.
Yeah. Thank you for giving us this lecture.
Salut Christophe.
Salut.
I do
Yann.
not understand. Ah, okay.
Hi, Hyungbo.
Hello, Hiroshi. Hi.
Good, good.
Yeah.
Thank you for being ready for presenting your talk.
Thank you for the invitation, Hiroshi, actually.
We are in streaming and now I am also registering. Okay. Hi, Christophe.
Hi, Claudia.
So good morning, everyone, audience in Asia, Europe, and all around the world. Good afternoon, good morning, and good very early morning. It's my pleasure to welcome again our guest speaker for our joint IFAC IEEE CSS webinar series on nonlinear control systems. And today we have the pleasure of having Professor Hyungbo Shim from Seoul National University, who will present a lecture on coordinations of heterogeneous multi-agent systems via blended dynamics theorem. Before we enter the main lecture, let me introduce Hyungbo Shim. Hyungbo Shim is a professor at Department Electrical and Computer Engineering, Seoul National University, Korea, where he received bachelor, master, and PhD degrees from in 93, 95, and 2000, respectively. He was a postdoctoral researcher at the UC Santa Barbara and a faculty member in Hanyang University before he joined Seoul National University in 2003. He is currently also the general chair of IFAC World Congress in 2026, which will be held in Busan, Korea, and among many other services that he has done in IEEE and IFAC. His research interest includes stability analysis of nonlinear systems, observer design, disturbance observer techniques, secure control systems, and synchronizations for multi-agent systems. So without any further ado, I'd like to invite Professor Hyungbo Shim to give the lecture, and I'm going to allow you to share the screen.
All right. Thank you very much, Bayu, for your kind introduction. And I really appreciate all the organizers, Claudio, Bayu, Hiroshi, Andrea, for this honorable opportunity to share what we have been working on. And I also thank all of you for your presence here today. Today, I'm going to talk about the coordination of a heterogeneous multi-agent system, as Bayu introduced. Basically, I want to try to answer three questions. So the first question is, how does consensus give rise to the emergent behavior? Second one is, how does consensus give rise to the robustness of group behavior? And we also want to answer the question, how different agents perform different tasks in coordination. And during this procedure, I also want to present a few design examples that support our discussion. So over this talk, whenever I say consensus, that means synchronization, which means all the states of every agent will get the same as time goes on. In this presentation, actually, simplicity is pursued rather than the generality and rigor. So some technical regularity and assumptions may be omitted. And I do apologize that I was not able to include all the related work due to the space limitation. So the first question is, how does consensus give rise to the emergent behavior? So regarding that, I want to emphasize the emergent behavior is an outcome of diversity and consensus. So these two things are actually conflicting notion, right? So the diversity is being different and the consensus is getting the same. So what I really mean by this is for the heterogeneous multi-agent system, when we press them and when we enforce the consensus, then the emergent behavior arises. To see this, let's consider this n different agent. So here script n means the set of index. And here fi is the node vector field that may be different from others. And this time t allows this vector field may depends on the external input or external command or disturbance. And here ui is a signal enforcing the consensus. So for this signal, please let me assume only one assumption, which is A star. And that means there exists a positive vector theta. And this theta, if we sum all the elements, it is written in this way. And it's summed to 1. And also the linear combination of the input signals is all time 0. Well, actually, there does exist some input signal which satisfy A star, but we will get to this point later again. But the point is here under this assumption, now we can show the enforce the consensus yielded some emergent behavior. So under that assumption A star, we have a theta vector. And based on this theta vector, we can always find two matrices Q and R such that this matrix are inverse to each other. And then we can use this matrix as a linear coordinate change over the whole multi-agent system. So let's just stack the individual states x1 to xn like the x, and then apply this coordinate change to get the ZO and Z tilde. So ZO is nothing but the linear combination of individual of agent, and Z tilde is all others. By the way, in order to be precise, I had to write the canonical product everywhere, but that messed up the slide. So please allow me to omit this thing. If you are not comfortable, you can just regard this n is 1, but I think you will allow me to do that. But anyway, so here we have this vector and this vector. And what is the inverse? Well, inverse is this. The x is this. Or we can write xi, the individual agent, is sum of ZO plus the ith row of this R times Z tilde. So what does it mean? This means that Z tilde is the measure of consensus, right? When Z tilde is 0, then we get consensus. Otherwise, it's not 0. So this is a measure of consensus. Once consensus is achieved, then the behavior of xi just the same as ZO. So what is the dynamics of ZO? Well, if we apply this linear change, then we get this. Here, we don't have to pay attention to Z tilde dynamics because we assume that this input U will enforce consensus. And then let's look at this part. So here, if Z tilde becomes 0, the dynamics left is the same as this one, right? So when Z tilde is equal to 0, ZO is governed by this dynamics. This one is somehow emergent one, right? Because no node dynamics looks like this one. This is kind of putting together all the dynamics piece by piece to make this one, right? This is a linear combination of each node dynamics. So in that sense, I'm saying some emergent behavior will arise because individual xi will follow ZO, and ZO will be governed by this dynamics. So that's the way how some emergent dynamics arises. So please let me name this dynamics as a blended dynamics. Actually, making a name is not a good thing because there are too many things to memorize. But we will see this will be convenient for us to use this kind of a naming. By the way, the same thing was found independently by the Elena Pantley and the Antonio Loria. And then they name it as dynamics as emergent dynamics. Well, actually, the definition is slightly different when it comes to the output coupling, but in this case, they are exactly the same. We also used a different name, which is average dynamics before, but we found that this terminology is already reserved in the averaging theory, where the vector field is time averaged. So we had to change the name to this blended dynamics. Anyway, so the perfect synchronization is, of course, not very practical. So we need some kind of stability to make every things in a good place. So we can say in this way, the assumption one is there exists a consensus enforcing signal U, which satisfies A star, and enforcing the approximate consensus in the sense that Z tilde eventually gets small like this. And then we need some kind of stability, which looks like this one. For all such Z tilde as above, the solution of ZO, which is a solution of this dynamics, where Z tilde plays the role of input, and S is the solution of blended dynamics, starting from the same initial condition, they will get similar. They will get close to each other eventually. So that's a kind of a stability notion to the blended dynamics I'm claiming. And then with these two conditions, we can get the result. So individual agent will follow the behavior of the blended dynamics with some small error. Actually, all these things, maybe in most cases, this is semi-global result. But today, I don't want to go into details in the underlying set for simplicity. So we will omit that part. Anyway, from now on, for the time being, we will look at the actual input UI that satisfies A star and enforces the approximate consensus, and also some stability condition imposed on the blended dynamics and some consequence of them. So let me begin. So this is the first simplest case, which is the linear diffusive coupling. So here, the input signal UI looks like this. Here, the K is a positive constant, which we call the coupling gain. And this Ni is the index set of the neighboring agent of agent I. And then we have some differences here. If we assume the underlying communication graph is strongly connected, then this linear coupling and graph satisfy the A star with the normalized left eigenvector theta of the Laplacian matrix that corresponds to the zero eigenvalue. Now, regarding the stability of the blended dynamics, let's impose the contractivity in the sense of Lowe, Miller, and Slotin in 1998 Automatica paper. The benefit of this one is we don't need to assume the existence of the equilibrium point or compact attractor. That's useful because T may represent some external input or command. So under this contractivity assumption, we will get the result. For arbitrarily small epsilon, there exists some threshold K star. If the coupling gain K is larger than that threshold, all the behavior of individual agent looks like S with some small error epsilon. Okay, so that's our first result. If you are not very satisfied with this epsilon error, then of course we can borrow the idea of the sliding mode control by introducing some sign coupling like this. In this case, the underlying graph must be undirected and connected. So in this case, the A star hold with 1 over n, which is the theta vector. And then the blended dynamics is just the average of the vector field. And again, if we impose the contractivity, then we got the zero residual error links. But we know this sign function is not very practical because it's difficult to implement the sign function exactly. In that case, maybe we can borrow the idea of PI control, where the integral control will eliminate the residual, the steady state error. So this is a PI coupling. Here, instead, we now assume the existence of the exponentially stable equilibrium point S star of the blended dynamics. And then let's look at how it looks like. Here, this Xi is the integral state, integrator's state, which integrates this diffusive coupling error. And this Xi is used in the coupling. And the cost to pay for this coupling is we need to communicate this Xi states to the neighbors. But the outcome is every agent will converge to S star so that we have a zero error. We can also use some kind of nonlinear coupling idea borrowed from the funnel control in the literature. So the funnel control is the following. We can consider some funnel function pi t like this. At the initial time, the size of pi is large enough to contain all the differences like this. But as time goes on, it becomes very small. Also, this mu function is an odd function, 0 is 0. It goes to infinity as it goes to 1. So initially, this error starts within this funnel, but this error goes to the boundary of this funnel function, funnel boundary, then this function becomes infinite. So in that way, they can enforce to capture all the differences within this funnel so that we can get the enforced consensus in the end. So again, under some usual assumption, we get this kind of approximate error. In the discrete time case, we can get a similar result. But so far, our idea to enforce consensus is using the large coupling gain. But for the discrete time case, we know that large coupling gain will lead some instability of the discrete time system. So here, our idea to enforce the consensus is that we do care more about consensus rather than the progress of the node dynamics. So what I mean is we have two cases, and in most cases, we just do consensus, 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 but every k times we progress along the node dynamics, and again, consensus, 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 and progress. So in this way, under the same assumption, by the way, this is the discrete time blended dynamics, then we get this convergence. So here we just compare this xi with the solution of blended dynamics at every k times, but other than that, the result is similar. The next one is of a hybrid type. So this coupling is actually motivated by this figure. So each edge is time to time activated. Whenever it is activated, the information is delivered, and the received node will update its internal signal or jump of the internal signal. This kind of things can be properly described by the hybrid system framework by Andy, Ricardo, and Rafael. But here for simplicity, let me just use the Dirac delta function like this. And then in order to decide when to activate the edge, we assume that every edge maintain their own timer, which is tau ij, and its speed is proportional to k, which is constant. And then it belongs to 0 and 1. It is just increase. When it reaches the value of 1, then it jumps to the lower value, less than 1. So in this way, if we increase the value of k, then we experience more and more frequent jump. So under this idea, under the user assumption, now we have the similar convergence result as before. Okay. So far, we talked about all the internal states are communicated, right? But now let's think about some portion or the part of the state is communicated like this. So in this way, we call this xi is the output of this system. Since xi is communicated and since xi is updated, so we can expect only xi reach the consensus, right? Well, particularly this gi can be considered as an external input in this way. Then we can easily imagine that our blended dynamics should look like this one, right? So here, this gi is just left as it is. So this is still the multi-agent system, right? And then we see that gi is interacting with the S dynamics regardless of the underlying graph. So they can directly interact with this S dynamics here. We call it as a blended dynamics. This is slightly different because in this paper, they assumed they also took some average of this part and then they call it as a emergent dynamics. That's a small difference. Anyway, if we assume the blended dynamics has an asymptotically stable complex at A, then we get this kind of approximate result, which basically means that all the xi's are approximately consensus, but all the others are just as it is. I mean, they just attracted by this set A, but not moles. Okay, so that's the coupling. All right, so far we looked at several real input which enforcing the consensus. But now let me just give you two more ways to characterize the blended dynamics. The first one is taken from this Meganem, Pentley, and Loria paper. What they said is, in the case of linear coupling like this, if K is increased, then the multi-agent system exhibits 2 time scale behavior and becomes singularly perturbed system. The reason is the Laplacian matrix has a 0 eigenvalue, so there are some time separation. And the boundary layer system is always stable as long as the graph is connected. So with large value of K, the consensus error quickly goes to 0. And then the remaining dynamics, which is a quasi-steady state subsystem, is the blended dynamics. It's one way. Another way is we can look at this multi-agent system as an input-output system. So this is input. And the output is defined in this way using the Laplacian matrix L. Then if we compute the 0 dynamics over this dynamics, we will see that this one appears, which is the blended dynamics. So that's another way to characterize the blended dynamics. Okay, so let me summarize. So far, we talked that we emphasized that when a group of heterogeneous multi-agent system is enforced for consensus under A star, then the emergent behavior arises, and which is governed by the blended dynamics. I told you some emergent behavior. So here's one example. So what are these agents are doing? That's the question. So here, most of them are just integrating number 1, and one agent is integrating minus x plus 1, and they communicate. So what is the outcome? Well, to see what they are doing, we can compute the blended dynamics, which looks like this one. And then we realize the S converges to the N, which is the number of agents, right? So with sufficiently large coupling gain K, individual agent state will converge to N. So this network is actually distributed network size estimator, right? So this role is emergent one, I'm claiming, right? Because no one is counting the number of N, and it's not easy to expect this kind of behavior will arise eventually. One more thing which is interesting is here, this agent is not stable, but this agent is stable. So stability is somehow traded along the network, right? So that's another interesting point, I guess. Actually, this observation let us think in a reverse way to come up with an idea of designing multi-agent system or some distributed algorithm, which is the following. At the first step, we build the desired dynamics. What I want, we just build. Then check this F desired is decomposed as a linear combination of small pieces. If so, then we can assign each piece to each agent and then enforce the consensus. So that's the way how we can build a heterogeneous multi-agent system or distributed algorithm. So here's a practice. So the task is, let's design a distributed observer for this linear system, and there are capital N different sensors. So first step is to write down the desired observer, which is just the standard state observer, and to see whether it is decomposable. And it's actually decomposable using the Li is the ith column, Ci is the ith row, and this Yi is just the ith sensor. And then since this is a decomposed, then now we know the distributed observer should look like this one, right? Here they only use the Yi measurement, but here N means we are going to take the average, in the blended dynamic, right? And then it works well. So that's the way how we can develop some kind of multi-agent system or distributed algorithm. Here again, one other observation is we didn't assume the detectability of A and Ci. So maybe individual one is not stable. There are no observer gain Li which stabilize this system, right? But stability is actually emerging as long as A and C is detectable, right? So that's another interesting point in this line of thought, I think. Here's another application. So regarding the distributed optimization. So in the field of distributed optimization, a typical problem is to find the optimal X, which minimize this capital F, which is a separable function. And then one of the finding this solution is to apply the gradient descent method. And since this is separable, the gradient descent method looks like this one. Then if we think this is a blended dynamics, then we can easily come up with what should be the distributed gradient descent algorithm, which looks like this one. That's simple, right? Here, I want to emphasize that we didn't assume the convexity of individual Fi, right? As long as its sum is strongly convex. As far as I know, this direction of research is not active in the field of distributed optimization because most of them require this Fi is convex. The same idea also applies to the momentum method, which is a second order method. So here, the interesting point is we apply the output coupling, but I think I have to skip that because I already spent too much time for this first part. So let me skip this page. Okay, so let's move on to the second question. The second question is, how does consensus give rise to the robustness of group behavior? So here I want to emphasize that the robustness comes from the consensus plus large number of agents. And this idea was already published in the paper of how synchronization protects from noise. So in this paper, they considered the identical multi-agent system, but individual agent is affected by the stochastic noise like this. And then they define the average value ZO. Then the ZO is governed by this equation. And here, this is the average of the stochastic noise, but this can be equivalently described by the same stochastic noise of the same distribution, but its amplitude is divided by square root of n. So what does it mean? If you have a large number of agents, oh, by the way, this stochastic noise is independent and identically distributed noise, right? Okay, so based on that, if n is increased, then the intensity of this noise goes to 0. Okay, so if we consider the heterogeneous multi-agent system here, and if we enforce the consensus, then this Ci becomes ZO, then this dynamics is nothing but the blended dynamics. So that means blended dynamics gets less sensitive to IID zero mean noise and disturbance as n gets larger. Then the enforced consensus transfer this insensitivity of the blended dynamics into the insensitivity of the individual agent. So this is one example how robustness of the group behavior may arise. But today, based on the same philosophy, I'd like to also talk about some more robustness, like robustness of the group behavior against malfunctioning agents and against the production imperfection. And also, I want to discuss the robustness of group behavior against joining and the leaving agents. So the first example, let's talk about some coupled oscillator. So we consider a group of oscillators whose magnitude, phase, and frequency are all different, and even some agent may not even oscillating. So as an example, I took the well-known Van der Pol oscillator. In this Van der Pol oscillator, they have two parameters, mu and nu. And this Van der Pol oscillator has a stable limit cycle if and only if these mu and nu are positive. And of course, these values also decide the magnitude and frequency. So if they are all different and they don't have any coupling, then the simulation result shows that their behaviors are all different like this. And even this pink agent is actually converged to the origin, meaning that it's somehow malfunctioning oscillator, right? But if we introduce some coupling, then they look like synchronized, and they somehow the malfunctioning pink agent is revived, right? It just works well in this way. Okay, so from now on, let me just show you some theorem behind this simulation, which is this. So this kind of a Van der Waals oscillator, approximate consensus is achieved by this linear coupling, where this y is just x plus x dot. So in this sense, this is output coupling, right? This is second order system, but instead of communicating two states, we just communicate one signal. Maybe this is appropriate for the biological systems. But anyway, the consensus error goes to 0 as k goes to infinity. And all these things hold under the assumption that these two quantities are positive. So they are average of individual parameter. So in the next page, please let me prove this theorem in one page. So in order to prove this theorem, we just took the state. So I want to realize things in the state space, but this is the key how to get the state. So here z is x, y is this sum. Then the individual agent looks like this one. So here you see the y is communicated. So the blended dynamics in this case must be this one. So we took some average of this vector field here. And then this is still the multi-agent system, right? But very fortunately, this part is a stable linear system affected by the same signal S. So as time goes on, this Zi will become a single trajectory Z. So as time goes on, this blended dynamics tends to this second order system, right? And then because all this Zi becomes a single trajectory Z, so now this summation can go inside the bracket and it looks like this one. So now if we compare this thing with the individual one, then we, as I said, these two parameters must be positive in order to have a stable limit cycle. So this average is a positive in order to have a stable limit cycle of the blended dynamics. So that leads to our conclusion in the previous page. So what is the lesson? The lesson is I assume these two parameters are positive. I didn't assume individual ones should be positive. That means even if some of them are negative, which means that agent is a malfunctioning agent, that can be compensated by other majority of good neighbors. So here I can summarize our finding in this way. Robustness arises when there are dominating number of good agents. That's because the blended dynamics looks like this one. So I think this is particularly interesting to me. So maybe in the long future, when we have a multi-agent system and some agent is malfunctioning, then the typical way is to figure out which one is malfunctioning and replace it. But if it doesn't work very well, then maybe we don't care. We just pour or deploy more good agent and done. So I don't know, but yeah, this is somehow, well, I think this left one is engineering style solution and this right one is biological style solution. But of course, this is just imagination. Anyway, so the next one is, let me talk about the robustness against the imperfect production. So what it means is that actually everything is not perfect. So as you know, if the product is produced from a factory or some biological cells are created from the organs, maybe there are some imperfections. So, for example, in this kind of a Van der Waals oscillator, randomness in cell creation or imperfect production makes the parameters mu and nu is a random variable. So they may have some variance, sigma square of mu, sigma square like this. then how the multi-agent system becomes robust against the imperfect production? And the simple answer is by just a large number of agents, because if we take the average, then of course the variance becomes like this. So if large number of n, the variance gets smaller and smaller and smaller. So this can be easily observed from the simulation. So here we just tested of a coupled oscillator of 10 agents, and the generation is 3 times. So I just generate this random number and with the same distribution, And then the outcome is whenever I generate this network, their behaviors are all different. And even sometimes this is the initial condition, they converge to 0, so they don't oscillate. But if I increase the number of n, then eventually when it goes to 1000, they looks like a very same whenever I generate the network. So maybe this is the nature's strategy to ensure the robustness against the imperfect production. All right. So let me move on to the next issue, which is slightly different. So now let me talk about the robustness against the joining and leaving agents. So as an example, let's assume that we want to find the average of distributed data, which is distributed all around the node or the agent. So A1, A2, A3 in a distributed way. That's the question. And one of the well-known solutions is just to use the average consensus algorithm, which looks like this one. So we put all this data to the initial condition of the agent, and they just run the average consensus in this way. Then as time goes on, all xi goes to the average of them. So we solved this question. Another way is to employ the blended dynamic theorem. So we prepare this kind of agent, and the blended dynamics is something like this. As time goes on, s goes to this number, and so xi also goes to this number. So which one is better? Well, I can claim that actually putting the information in the initial condition is not good, because communication noise, communication disturbance may disturb this final value. But more importantly, let's say after the synchronization, the agent 3 leave the network. Then there are no changes, because these things are all 0, so they remain there. But here, if agent 3 leave the network, then the blended dynamics is changed so that this value is also changed. So it can always, give you the correct answer regardless of the joining agent or leaving agent. So let me summarize this lesson in this way. The algorithms designed by the blended dynamic theorem are initialization free. It doesn't depend on particular initial condition. It is because the blended dynamics is stable, by which any initial condition will be forgotten eventually. Therefore, if a new agent joins the network with arbitrary initial condition, or if an agent leaves the network with some amount of internal state, it doesn't cause any trouble. And the group behavior is still governed by the updated blended dynamics. So we can call this kind of property as a plug-and-play ready algorithm. Another lesson is, if you design a distributed algorithm that processes some information in the agent, please do not put your information into the initial conditions. Instead, you can put it in the vector field. So based on this philosophy, we were able to construct several distributed solvers for least square, median, max and mean, p-quantile, and so on. They are all available in the literature. I particularly want to emphasize this median operation is important, because the median operation is a way to have a majority voting or some outlier rejection or something like that. So that can be solved in a distributed way. That could be somehow interesting. By the way, this way is one way to make the open mass in the literature. Okay, so let's move on to our last question. How different agents perform different tasks in harmony for a global goal? That's the question. For that question, I just want to emphasize, in order for heterogeneous agent to work in coordination or harmony, there should be some hidden variable that are in consensus. And this sounds so natural, and there are no surprise. For example, today, we are all different. We live in a different country, but we are in a coordination because we are attending the same webinar in this way. So what is the hidden variable in our case? And the hidden variable is the clock, right? So it's easily guessed. So actually, in this work, I think figuring out this internal variable is sometimes easy, sometimes not easy. So I just want to show two examples from now. So the first example is economy power dispatch problem for smart grid. So we think this kind of a electricity network. So each agent I consumes the amount of power Di, and they can generate the power amount of Xi by the generation cost Ji of Xi. And they want to minimize the total cost. So meaning that individuals want to decide their own demand and their own cost, and they want to know the optimal generation amount, XR1, right? So this is nothing but the resource allocation problem. So we want to find all these variables which solve to minimize the sum of the cost function under the constraint that the total supply is equal to total demand for all time. By the way, these are time-varying variable. And this individual Xi should satisfy some individual constraint like a minimum allowable generation or maximum allowable generation and so on. And this problem is actually have a standard solution if we can solve it in a centralized way, which is we can introduce the Lagrange multiplier and we define the dual function G in this way. So here's a Lagrange multiplier. And we can figure out, we can maximize this dual function and get the lambda star using the gradient ascent algorithm in this way. And once we find the lambda star, then the optimal individual Xi are obtained in this kind of a closed form. So here this equation is not important. I just emphasize they can decide their individual optimal value from the lambda star. Actually, the lambda star is somehow some variable that should be in consensus among others. If we want to solve this question in a distributed way, then all Xi's are different. The optimal value are different, but they should be in coordination. They should be in harmony for the global optimality. So in that sense, lambda star is somehow plays the role of a hidden variable. But also, fortunately, this dual function is separable. We can easily exchange this infimum summation, and then we can define this part as an individual dual function Gi. And this gradient ascent is also the separable in this way. So the distributed algorithm looks like this. So individual agent just run this dynamics using the PI coupling, which enforces the consensus. And then once they have this lambda I, they put this closed form and they get this Xi. So this works well. The good thing is that there are no private information exchange because individual one only use individual function Gi, which is private information. The only information that is shared is the Lagrange multiplier lambda over the network. This is also the initialization free algorithm because we are based on the blended dynamic theorem. By the way, as I said, in this case, the hidden variable, well, maybe it's not hidden, but the variable that should be in a consensus is the Lagrange multiplier. Okay, so this is our last example. So let's think about the distributed stabilization of a multi-channel linear system. Here, I want to stabilize this linear plant, which has a multi-input and multi-output. This is somehow conceptual drawing. So here we see some input channel has a green color, and the output channel is a pink color. So what I mean is we have a bunch of control agents. The control agent can randomly move around this area. And then when they happen to land this site, then they can measure this Yi and they generate the control UI, but they don't know the others YI, and they don't know the others CJ and BJ, and so they only know, they can read from the surface this matrix A and BI and CI. So using only this information, they need to generate the feedback gain. They need to generate their own controller. So this is a kind of a self-organization, right? The good thing for them is they can communicate with their neighbors. There are no leader, no center. Everything is distributed, but they can communicate with their neighbors. Of course, they can leave at any time, like a battery is run out, and they can leave. So maybe there are some idling channel, but it's okay. So this is the problem setting. And then the problem is we want to design the identical control agent for stabilizing of the plant. So why identical? Because we still a little interested about this kind of a pouring or deploying the identical agent. There are no designated location where you should go this location, you should go this location. It's not like that. It's just randomly deployed. They just landed any location and they start the stabilizing task. Okay, so in order to solve this question, basically we want to use the separation principle idea. So we want to build the distributed observer and the state feedback. But it's a little bit complicated, so let's go step by step. The first step is, for the time being, let's assume that there are fixed graph, so no one is joining or leaving, just fixed. And this number, and every agent knows that. And moreover, every agent I knows Fi and Li. So what are they? Well, Fi is just a stabilizing feedback gain, and Li is the stabilizing observer gain, right? So we just assume that everyone knows Fi and Li for them, right? Based on this assumption, the problem is solved if every control agent runs this dynamics, which is the distributed observer and state feedback. So here, this is the the copy of the plant, right? Where, of course, each agent doesn't know the other's Fj. So instead of using Fj, they just multiply by n, but we know the secret, right? So we will just take the average. So this is not a big deal. And here, we already know the distributed observer should look like this one. And here is some communication. And Fi is just a state feedback gain. So it should work well, right? So of course, if you compute the blended dynamics of everything, then you see that the blended dynamics is just a standard observer. So S will converge to the real plant state X, and so that individual one also converge to S, and then the plant is stabilized in this way. So not surprised, right? But here, let's eliminate these assumptions. First, actually figuring out n is easy because I already told you how to figure out this number of n in a distributed way. But here, this is difficult. I mean, in order to choose F1, this F1 is also affected by F2. So all these things cannot be chosen independently. They are related, right? So they should be designed in a one shot and then distribute. It's difficult. It violates the distributed optimization, distributed operation. So here we need some idea. I mean, everything should be in coordination to stabilize the plant. So what could be the hidden variable, which should be in consensus to achieve this kind of coordination? And the idea comes from this bus algorithm, which was developed by my PhD student before, the Taegyo Kim. And he looked at this thing with AB is controllable and beta is large enough. Then we can solve this Lyapunov equation, green X. Then the stabilizing F can be computed in this way. Then A plus BF becomes Fourier. Okay, that's just a usual thing, I think. But if we look at this equation again, then F1 to Fn depends in this way. So that means as long as we know, every agent know the green matrix X, then they can individually multiply BI, then they can individually figure out FI, right? So the key is figuring out this Lyapunov matrix X, which is the hidden variable that should be in consensus for coordination. Okay, and the second question is, can you solve X in a distributed manner? Actually, the secret is this green X contains every information about BI and BJ because this one is here. So it is still not a distributed computation. But instead of solving this static Lyapunov equation, let's solve this kind of a differential Lyapunov equation. And then we can treat, by the way, this blue X will converge to green X because of the stability of A plus beta I. Okay, and then we can treat this equation as a blended dynamics. And we know how to distribute it, this procedure. So again, I'm writing here, and then this looks like this one. So if we treat this one as a blended dynamics, we can construct this kind of a distributed algorithm, which will converge to the green X. And then FI can be constructed in this way. Okay, so the same thing should do some observer gain Li, then I can skip that. So overall, now the pink control agent should look like this one. So here, this is a size estimator. And here, this is finding the green X and Y. So then this is a distributed observer, and we have a state feedback. So again, this is a distributed operation, plug and play ready. And last thing is I just emphasize the hidden variable that should be in consensus is the Lyapunov matrix, or we can say it's a control Lyapunov function for that. I think time's up, but this is just a simulation result. So the task is this orange box should move to the goal. An individual mobile robot only can push or pull, but there are no intelligence in them. So they just randomly move around when they meet this object, and they start organizing their feedback gain and start feedback control. So you see the red one is moving around, and green one is just battery is one out. So they just leave the object. And so. Okay, so let me summarize. I just try to discuss 3 questions, and I want to emphasize 3 points. And at last, to design a distributed algorithm or the multi-agent system, maybe thinking the blended dynamics may help from the beginning. And I really think, and this works is actually a tribute to my former student and my collaborators, and I also thank to the sponsors. Thank you very much for your attention. That's it.
Thank you, Hyungbo, for a very inspiring talk and a very clear one. Now the floor is open for the discussions. I have asked the audience to put their initial questions on the chat, and I have noticed that there is one question from Christoph. Christoph, maybe you can ask your questions.
Yes, I can ask directly to Hyungbo if you don't mind. Thanks, Bayu, for giving me the floor and the opportunity to ask this question directly. Thanks a lot, Hyungbo, for the great and very clear talk. It was very. I have many questions, but maybe I can just ask one naive one. Can you come back on slide 10? I guess it is John Ward Neil.
Yes.
Slide 10, it is
Yes, okay.
Yes, so yeah, here. So I see that there are some discrete dynamics due to the fact that you are a timer and you have some jumps of the timer variable. And do you think that you can develop a general theory for hybrid systems, when you have a discrete and joint discrete and continuous dynamics with constraints on the state, as done by Andrew Thiel, Rafael Goebel, and Ricardo Sanfelice in using a very general hybrid framework? Do you think that you can mix general hybrid dynamics like that?
Okay, so actually, as you see in here, this outcome is based on the singular perturbation theorem of some class of hybrid system. So there we have a continuous dynamics and the jump dynamics. But the singularity, I mean, singular perturbation, the two-time behavior comes from that the jump is becoming more and more frequent. And the
Right.
jumps will give you some boundary layer behavior, right? So we were written in that way, which is under review. By the way, this paper is also somehow in that direction, but it's more general one
Okay.
is the second one. But
Okay.
so this is one application to the blended dynamics, but we have a more general framework. Maybe that answers your question.
Okay, I will check the CDC 2021
Mhm.
paper. Okay, thanks a lot.
Okay, thank you, Christoph. And I noticed that there is also another questions from Anil. Anil, would you like to pose your questions?
Okay. Sure. So Hyungbo, thanks for the talk. My question was about your meta theorem. You give two conditions which ensure some sort of convergence, right? And you also give examples where we can actually have convergence to zero, not just practical convergence. And you did not mention anything about the rate of convergences. For example, typically we are looking for exponential convergence. Do you think this has more to do with something like condition one, where we can always choose a control action to have desired rate of convergences, or do you think it requires strengthening condition two? It needs some sort of additional structure on the vector fields to have this kind of desired behavior?
So yeah, so I think that's a good question. So regarding the convergence, like asymptotic convergence or the exponential convergence, I think the condition one is more related because that decide your convergence rate. But these two things are correlated. So actually in these old theorems, we use Lyapunov function and so on. So they are related. So it depends on what is your final goal. You want to, let me see, if you want to go to the equilibrium point as a star, something like this, then of course the convergence rate or blended dynamics is also important. But your goal is just emergent behavior arising, then just the consensus convergence rate for the consensus is important. So it, of course, depends on, but they are somehow related because in the Lyapunov function, they can trade the convergence rate between those two things.
On the previous slide, when you had the signum coupling, you get we don't need the existence of an equilibrium point here, right? We get convergence to the trajectories. And in this case, the convergence is not exponential, I'm assuming, right?
Right. So in this case, convergence is not right, because sine function, well, in this case, you get the finite time convergence is guaranteed using this kind of a thing. So what I mean is your synchronization error will get to the synchronization manifold within finite time.
Well, that's the property of the signum. Okay.
Yeah, that's property of the signum. Of course, in this case, the F vector field should be bounded. Otherwise, you cannot capture those sign, but
okay, so the both play a role, condition one and condition two, when you establish the rates. Okay, thank you.
Okay. Maybe I have a short question, Hyungbo.
Yes,
so
please.
I think you presented a general design framework where we should try to define a desired blended dynamics, and then you can move on to the design of individual control. But if I recall from your first part of your talk, the contractivity or exponential stability is required. So when you describe the desired dynamics, do you assume that, or actually it's not being assumed? Whether incremental stability is enough or not?
Well, actually, you're right. So here at this stage, the desired behavior should have some kind of a stability notion. It can be contractivity, or it can be some having exponentially stable or asymptotically stable compact attractor, depends on your application. But stability is somehow necessary in order to have a long-term behavior. As you know, in the singular perturbation theory, for the short time behavior, it's okay. You just push the the fast dynamics to the quasi-state manifold, then you can endure for the short time being, but that's rare case. I think in most application, you need a long-term behavior. So you need some kind of a stability of the blended dynamics so that you get long-term behavior, which is somehow stable one. So again, you are right. When you make this dynamics, we need some kind of stability.
Okay, but I think if I recall in your first part, you always assume contractivity, which somehow
Right.
implies a bit
Right.
of local exponential stability.
Okay.
If it is only incremental stability, is it enough? So instead of
So here, when we just use the Lowmiller-Slotin contractivity, which means somehow looks like a quadratic condition.
yes,
It's a little bit strong. Yes, it's not like an incremental stability. So we are not yet at that level. So for the
okay,
contractivity,
but
we need
there's an open problem there.
Right, right. Yeah.
All right, so I think there is no more questions, and we are also close to the end. I would like to thank again Hyungbo for a very nice and clear presentations. And all of the material is going to be online very soon. And I would like to also announce the next talk, which will take place in March. It will be presented by Professor Kirsten Morris from Waterloo. So please monitor your emails to get announcement and detail on that.
Yes, that's the information of the webinar. We will post it right after this talk, so everyone can check the webpage. Thank you.
Thank you again, everyone, and I wish you all a very nice afternoon, evening, and morning.
Thank you.
Thank you, Young.
Thank you, Hyungbo.
Thank you.
Very interesting, clear talk. And yeah, and also many of you will submit papers to Micron 2024. Yeah.
We will. It will come from me.
Yeah, 2024 Micron deadline will be 8th of March. Yeah.
Bye.
Bye-bye, Hyungbo. So
Very interesting talk and clear. And yeah, I have many questions that I will ask question when I can sort out my questions. Thank you. Thank you, Califano. Bye.